Good day and welcome back to the fourth video on the subject of double integrals. In the previous three videos we introduced the concept of a double integral, its geometric interpretation of this net difference of enclosed volumes, and we investigated it from that perspective. In this video and a few of the upcoming videos, we are going to explore more of a quantitative approach using what we call iterated integrals. So let me start by just jumping into exactly what an iterated integral is. It will essentially be an integral of one of the two forms given here. And note what we're seeing is that we have two integrals, one with respect to y and x for a function of those two variables, ordered in either one of those two ways, and how we think about this is from the inside out. We would first evaluate the inside integral with respect to y, and then the outside integral with respect to x, or vice versa for the right. So the big key observation to get started is we work from the inside out. It's also worth mentioning that we are now to the point in the course where integration is going to be extremely important. So I'm going to suggest that we all need to be familiar with the standard techniques of integration. And this is something that we hit on previously when we were discussing vector-valued functions. The things that I would recommend making sure that we are familiar with would be common formulas, along with, I'll say, the two methods of integration that we probably use the most. So the first would be substitutions, and then followed closely behind would either be integration by parts or maybe even partial fraction decompositions. These are all certainly fair game to come up. And you can find related resources to help you with these things in the course materials section on Canvas. So let's go ahead and just jump directly into an example. For this first iterated integral, we are integrating a function of two variables, 4xy, and remember we work our way from the inside out. So the first thing that we are going to need to do is integrate with respect to x. And let me go ahead and beforehand make a connection to our previous few videos. We can really think of this as being a double integral over a rectangle, so something of the form notationally, the double integral over r of a function f dA, where in this case, the function of two variables we are considering is 4xy, and the rectangle we are considering is 0 to 1 in the x direction and 1 to 3 in terms of y values. So let's go ahead and evaluate. So we work our way from the inside out, and similar to partial differentiation, if I want to integrate with respect to y, or in this case x, we treat y as a constant. That is, we are thinking of 4y as a constant, which is multiplied by x. So when we anti-differentiate a constant times x, we are going to get that constant times 1/2 x squared. And 4 over 2 would give us 2y x squared. And because it's a definite integral, we need to evaluate this from x equals 0 to x equals 1. And my quick bit of caution is to make sure that we're careful to write x equals 0 to x equals 1 so that we make sure we are substituting those values, the 0 and 1, into the correct variable. Once there are multiple variables present, a somewhat common mistake in the beginning that we don't want to make is substituting into the wrong variable. And furthermore, before we do this evaluation, let me just make sure we're all on the same page in terms of that antiderivative. So if I'm thinking about this 4xy, note that the partial derivative with respect to x of 2yx squared is equal to 4yx. So that 4yx corresponds to our integrand, and it justifies this partial integration that we have performed. So we now substitute in x equals 1, we put a minus sign, we substitute in x equals 0. So x equals 1 gives us back a 2y. If we subtract away what we get when we substitute in 0, that is just 0. Note that once we have evaluated the inside integral, this turns into a much more familiar setting. This is just a single definite integral from Calculus 1, which we can evaluate. The antiderivative of 2y would be y squared. We're substituting from 1 to 3. So we replace y with a 3. Minus sign, replace it with 1. 9 minus 1 gives us back the number 8, which, recall, has something to do with a net difference of enclosed volumes of a function of two variables sitting over a rectangle. But for now, we're going to focus purely on this computational aspect. What I would like you all to do is to go ahead and pause your video and to take maybe up to 2 minutes or so and see if you can evaluate the second iterated integral, where what we have done is just changed around the order in which we've integrated. We now have y on the inside, which means we would first integrate with respect to y, and once that is taken care of, we would integrate with respect to x. And hopefully you've taken a few minutes, and if you haven't, hit pause because I'm about to add some details to the screen. And hopefully your work looks similar. Note that, as usual, notation is extremely important in terms of showing equal signs, your integrals, dx's, dy's, things of that nature. So we first anti-differentiate with respect to y, 2xy squared. We evaluate from y equals 1 to 3. And remember, I write the y equals simply to make sure that I do not substitute in for the wrong variable on accident. That would give us, in this case, a 16x, whose antiderivative with respect to x is just a nice Calc 1 problem, 8x squared, substitute in 1, minus sign, substitute in 0. And hopefully an observation that you have made already is that the 8 agrees with our previous 8. And just to kind of highlight that observation, what we have observed is that if we start off with this first iterated integral, where we have an integral with respect to x on the inside and y on the outside, if we were to switch that order of integration, so put y on the inside and x on the outside, so now 1 to 3 with y, 0 to 1 with x, so we have to switch those corresponding limits of integration, that these two quantities will be equal. And it turns out that this observation is not a coincidence, but it's going to be very important that we are integrating over a rectangle, which is our current discussion, but we're going to move past this in the next section. And this leads us to a more general statement of this result, something called Fubini's theorem. So as mentioned in the previous example, Fubini's theorem, with some conditions on f, it's a reasonable function for us to work with. If we are integrating over a rectangle, and I once again cannot emphasize more strongly how important it is that we are integrating over a rectangle, then we can switch around the order of integration. You could do y first and x second, or x first and y second, depending upon the convenience of the integrals that you are working with. So once again, the big takeaway here is that the order of integration, in terms of which one is performed first or second, does not matter, and this is only over rectangles. And hopefully you're noting that I'm really emphasizing this point that we're talking about being over rectangles. So let's go ahead and look at an example and think about why we would want to integrate with respect to one variable before the other. In this case, we have the double integral over a rectangle of a function of two variables. So we have our starting point, this double integral over r. We have the function xy squared over x squared plus 1. And we have the ability to choose which variable to integrate with respect to first. And arguably in this case, I think it's probably equal difficulty. But one thing I would observe is that there's only a single y squared present, and with respect to y, we could really treat that x over x squared plus 1 as a constant. So it may be, marginally simpler to first integrate with respect to y. And the y's are varying from minus 3 to 3, and the x's from 0 to 1. So let's go ahead and evaluate. So if we first integrate with respect to y, we have the x over x squared plus 1, a constant with respect to y. Then we would multiply that by the antiderivative of y squared, so 1/3 y squared. And we're evaluating from y equals minus 3 to y equals 3. And that should be, y cubed dx. So we substitute in y equals 3. We put a minus sign. We substitute in y equals minus 3. So it's now the definite integral from 0 to 1, x over x squared plus 1. 1/3 is a constant. Y cubed is 27. And then we are subtracting away a minus 3 cubed, which would be minus 27. So in this case, note the minus a minus becomes a plus. So 27 plus 27 is 54. And 54/3 is actually a constant. And we can go ahead and simply pull that constant in front of the definite integral, which gives 54/3 times the definite integral from 0 to 1 of x over x squared plus 1. And something for you to think about is what technique of integration is now useful or applicable to this resulting Calculus 1 problem. And the observation that I would like to make is when you look at this denominator, x squared plus 1, you see essentially up to a constant, its derivative appearing in the numerator. So we should try u equals x squared plus 1. So du would be 2x dx. We have an x dx, which can be 1/2 du. So our integral would become 54/3. We can pull the 1/2 out front. We have a new integral with limits of integration that we need to determine of 1 over u. Now, this is where we have to be careful. Our original limits of integration are in terms of this variable x. But when we perform a substitution, we need to go from all x to all u, and all u would include our limits of integration. But remember, it's a very simple thing to change those limits of integration. We simply look at our substitution, and we find the u values corresponding to x equals 0 and x equals 1. So note, when x is equal to 0, our lower limit of integration, u is 0 squared plus 1, which is 1. Our lower limit. For our upper limit, when x is 1, u is 1 squared plus 1, which is equal to 2. Our new upper limit of integration. And I will note that in past classes, you may have gotten away with not changing the limits of integration with the substitution, but fortunately or unfortunately in here, we are always going to change those limits of integration when we have a substitution, because you can imagine with, say, a double integral and later on with a triple integral, it's really important to have that good notation and not have to worry about coming back and accounting for something later on. Now we simply evaluate this remaining integral. So we have 54 divided by 6, which is 9. Then we have the natural log of the absolute value of u from 1 to 2, which gives us 9 natural log absolute value 2 minus 9 natural log absolute value 1. You could certainly lose those absolute values. The natural log of 1 is a common value, which is 0, and we end up with 9 times the natural log of 2. And note, this is a very typical iterated integral. So we started off and we made the choice to first integrate with respect to y, purely because there was only one y term. So it made sense to kind of get that out of the way and save anything that looked like it could be potentially more difficult, i.e. involving a substitution, for when it was just a single, more familiar integral. Let me also make an additional observation, and maybe this is something that you were wondering. When we go back to that initial top step that we see, we made the observation that x over x squared plus 1 is a constant. And we've always said that we can pull constants outside of an integral. That is to say, it can be pulled outside of that integral with respect to y. And one way you could write that then would be the integral from 0 to 1, x over x squared plus 1, times the integral from minus 3 to 3, y squared dy dx. And then you might take it a step further and say, well, in that case, this definite integral with respect to y is just a numeric value, something about a net difference of enclosed areas. So how about we pull that out as well? And when we do, we've turned this iterated integral, this new type of problem, into two separate calculus 1 problems. That is, older, more familiar problems for us. And it turns out that this is something that we can do in general as long as you can separate the integrand function into a function of y times a function of x. And let's go ahead and state this as a property. If you are integrating over a rectangle, and I want to once again emphasize that importance, it has to be over a rectangle, and your function needs to separate into a function of x times a function of y. If that is the case, we can break this up into two single integrals. We could say we first integrate with respect to x, and then second we integrate with respect to y. The x interval is from a to b, the y interval is from c to d. And just to emphasize those important points, this is only over a rectangle when the function you are integrating, so let's say f of xy, is separated over multiplication. So g of x times h of y. And if both of those conditions are satisfied, you can break it up into two simpler single integrals to evaluate. In the next few videos, we will explore several more examples and see that this is not always the case, and just get some good practice with our anti-differentiation. So stay tuned and take care.